Welcome back as we begin our final chapter of material in our Calculus AB course. And to me, this is really, these are where the real problems are, where if you would use calculus today and doing some kind of research, you might be doing something when you're solving differential equations. Okay, so this is where there's a lot of activity going on. I know at Ohio State they have a biological statistics lab where they model cancer tumors, for instance, with differential equations. So anyway, the title is Chapter 10. We're in Chapter 10, and we're talking about differential equations and mathematical modeling. And again, a lot of the energy and the work in the field is trying to come up with the functions. You know, what makes some of our problems less than exciting is you're given a function. Here's a function, do calculus. Find how it changes. You know, add it up and find what the volume is, for instance. But a lot of times finding the function, actually finding that function is where the energy is. And this is one method for finding the function is we model physical processes with differential equations. Okay? We model it with differential equations, and you'll see when we solve a differential equation, we find that function we're looking for. So what is a differential equation? Differential equation is any equation involving a derivative. You could have this is a first derivative, y primed, or a second derivative. Down here, I'll give you some examples you've seen in other contexts. You'll see here's a differential equation. Force is equal to mass times the change in velocity over time. Well, this is merely another way of saying Newton's second law. Force is equal to mass times acceleration. If I know the force over time, I can calculate the velocity function. Here is a function that this is all those physics problems that describe projectile motion come from this single differential equation. This is a model of projectile motion in a gravitational field, and it says that the change in velocity over time is equal to negative times the gravitational constant. Okay, so this would be, in this sense, this would be the velocity in the y direction. Okay, and with this, I will show you, after we learn how to solve general differential equations, I think it's a lot of fun to go derive all those equations in physics that you use to solve those problems. And it all comes from that differential equation. Now, if you do physics problems, if you've taken physics, you know they always ignore a bunch of stuff. Ignoring air friction, in the absence of air friction, they use this model here. Well, what would you know, if you're talking about modeling, if you wanted to change the model, you see this little factor here. And it's a little hard to kind of figure out what this says. This is saying, for instance, if you jump out of an airplane. If you jump out of an airplane here on the left, okay, this model tells me that my velocity continues to increase, right? The acceleration is constant at minus g, and I keep accelerating faster, faster, faster as I hit the ground, okay? Whereas this model is more realistic, and it says I start off accelerating, but eventually I hit my terminal velocity. Terminal. I mean, I guess if I don't have a parachute, terminal in more ways than one. Terminal velocity, and this just says when I hit a certain velocity, I'm going to stop accelerating. Okay? So again, a model. A lot of times you model things with how things change, right? What does a derivative tell you? It tells you how things change. This tells me how velocity changes. My last model down here, let's clean this up. Here's a model we'll work with. Oop, that's kind of messed up. Let's fix that here, where I say the change in some quantity x with respect to time is equal to k times that quantity. This is going to be used to model bank accounts, um, exponential population growth. We got a law of cooling that we'll look at here. So here's a differential equation. This models a lot of different physical situations. Okay. So what's a differential equation? Differential equation is that when you see you got an equal sign and you got a derivative. Okay, now let's look at another one. Here's a particular differential equation. It says, it's a simple one, and it says here that the change in P is going to be my population with respect to time, is equal to P. It's equal to P. And let's do a little drawing here of this thing. And let's think if we can figure out what could go on here. You know, this basically says if I start with, I don't know, 10 rabbits, there's 10 here, right? This is T, this is P of T. And if there's 10 rabbits, my change in rabbits with respect to time in some units is 10. I don't know, let's say that's 10. When I have 10 more rabbits, well, then I have 20 rabbits, right? If I have 20 rabbits at this point, then this goes up, the PDT becomes 20. But if I have 20 more, now I have 40, and then my slope goes up at 40. Okay, if I have 40 rabbits, it's going up at 40, then I got 80 rabbits, then my slope goes up at 80. And you can see, as long as P is positive, can you read this now? This is what I mean by reading a differential equation. As long as P is positive, the rate of change is positive, right? And this means P, the slope of that curve is always positive, see? So it goes, this is positive 10, positive 20, positive 40, positive 80. It just keeps increasing. So you can see you're going to get a curve that's rapidly going off to infinity. All right, so you get a little idea of what that means, a little intuition. But getting back to what we want to learn to be able to do homework tonight, I'm going to tell you this. I'm going to give you oops, that's not what I want. I want to give me, I'm going to tell you P of T is equal to some C value e to the T. I'm going to say this is a general solution. Okay, this is a differential equation 1. This is a solution. What does a solution mean? That means if I plug it in on the left and right side, it should work. Okay, so let's take dPdt. dPdt is going to be what? Well, it's going to be C e to the T. That's the left side, okay? So I plug into the left side, I get that. How about if I plug into the right side? What's the right side? P. Oh, that's just C e to the T. Oh, well, look, left side of the equation equals right-hand side of the equation. So this is a general solution. General meaning, what's C? C could be any constant. C could be any constant. If I want a particular solution to a differential equation, I need to not only have the first part, the differential equation, I need a condition. So I'm going to say at P at time 0 is equal to 10. Okay? With that in mind, if I'm given a initial condition or a point on the curve, I'm given a point on the curve, then I would find P of T, or let's just say this, yeah, P of 0 is equal to 10 is equal to C e to the 0. It's equal to C. C is equal to 10. So I'm going to have P of T is equal to 10 e to the T. And we might call that, let's just call that a particular solution. So a solution to a differential equation is a function. And let me just remind you of things. So the first homework I'm going to give you, you're going to have to show, you're going to be given the solution, and you've got to plug it back in and show that it actually works. Remember, if I did something like this, x minus 2 on an algebraic, and I said x minus 2 squared is equal to 4, and you told me x equal 0 is, or x equal to 4, you know, these are solutions. If you said show that those are solutions, what would you do? Well, I'd plug into this side. I'd say 0 minus 2 squared. Oh, yeah, that's equal to 4. Check. How about 4 minus 2 squared? Is that equal to 4? Check. So just like algebraically, I can plug a solution into the left and the right side and make sure it works. To show that a differential equation works, I take a function and I plug it into both sides and it should work. So again, a solution to a differential equation is a function. That's a big point I'm hoping you get out of this. Okay, here's a question that you might get in your homework tonight where it says that show that this function y equal x minus 1 over x is a solution of this differential equation here. So how do we show it's a solution? Well, we plug in. First of all, I'm going to say what's y primed? Y primed is going to be equal to 1 minus 1 over x squared. Correct? Because I could say this is y is equal to x minus x to the minus 1. Oop, it's actually plus. There you go. I found an error. 1 over 1 plus x squared. Now I plug this in. I plug this in over here, and I get this is going to be x 1 plus 1 over x squared plus y. Well, what's y? 1, oh, shoot, y is x minus x to the minus 1 is then equal to 2x. So I'm just plugging into x, and let's see if these are working here. Here's x plus 1 over x plus x minus 1 over x equals 2x. Is that true? These are going to cancel. 2x is equal to 2x. That's a big old red check-a-rooney. Okay, so this function satisfies this differential equation. Okay, let's see if we can get another one here. Nothing hard about this. The point of doing this is just to understand what a solution means. Okay. For what values of r does e to the rx solve this differential equation? Okay, y, let's see here, we're going to go, y primed is going to be equal to r e to the rx. Y double primed is going to be equal to what? R squared e to the rx. Oof. Oh, this doesn't look easy to me. Now I'm plugging in here 2 r squared e to the rx plus r e to the rx minus e to the rx. I want that to equal 0. Okay, so I'm just taking I'm taking my solution, I'm plugging in, solving for r here. Looks like I have a constant factor that I can take out. If I take out e to the rx, I'm going to be left with 2r squared plus r minus 1. I want that to equal 0. Well, this is never equal to 0, so I want this to equal to 0. Okay, looks like I can factor this thing. Let's say 2r times r. Put a plus 1 here and a minus 1 there. That'll do it. Will it not? Yes, it will. So r could be equal to 1/2. So I want this to be equal to 0. R could be 1/2, or r could be equal to -1. Okay, very good. In the next section, we'll show you how to actually find the solution. Here, this whole thing was about understanding what a differential equation was and what a solution means. A solution means we found the function. This function works. But what we want to do is to give you a process to go from the differential equation to finding your own function. Anyway, we'll see you soon.